classification. So in chapter 1, we looked at some basic introductory parts of machine learning. We talked a little bit about regression and classification. And then in chapter 2, we explored linear and polynomial regression. So now we can look at classification. We're going to kick this off by talking about 3.1, which is binary classifier. And a binary classifier is going to be pretty simple, right? We're going to classify things as true or false, 1 or 0. And our goal here is to develop a model that we call the classifier that assigns inputs to one of 2 distinct classes, right? So just linear binary classification is simple but powerful, helps us distinguish between things that are typically kind of shown in a 2-dimensional field, right? So mathematically, we can look at it in terms of y hat. That's going to be our estimated output, right? That's our estimated target is equal to piecewise. It's equal to 1 if theta, which is our parameters that we learn, in this case, we're going to learn them through gradient descent, transpose x, which is our input data, plus our bias term, if we decide to add a bias term, is greater or equal to 0. All it has to do is be greater or equal to 0, and we're going to classify it as a true state. And then we're going to classify it as 0 otherwise. So if it's not greater or equal to 0, then we're just going to classify it as 0. So y hat labels are just going to be 1 or 0, but then we can classify that as oranges or bananas, or oranges and not oranges, or bananas and not bananas, things like that. All right, so despite its simplicity, these linear classifiers can actually be quite effective. And our goal is to kind of create classifiers that look like this. Right, so here we might have 3 models. We're going to call those models H1, H2, and H3. And these are the models that I train with my classifier. So if my classifier is going to take the form y equals mx plus b, right, or that equals theta plus theta x, so theta 1 plus theta 2, kind of in our terminology, any of these lines could fit that, right? So I can learn that line through gradient descent. All 3 of these lines actually classify these data perfectly, right? So, well, sorry, that's not true. H1 and H2 classify the data perfectly. So everything to the left of H1 is class blue circle. Everything to the right of H1, that's this vertical line, is class orange X. Same thing here with H2, which maybe is a slightly better classifier. And then H3 has a misclassification, right? If you assume everything above is blue circle, well, then these 2 items here are misclassified. But so that in general is what we're trying to look. So the challenge is, how do we obtain, hyperparameters? How do we get the hyperparameters? That's the challenge that we're actually going to embark on solving here. Now, we need a good data set. And one of the classic data sets that we use for classification is the modified NIST data set, MNIST, or MINST data set. And so it's the Modified National Institute of Standards and Technology. And it is a collection of 70,000 small images of handwritten digits. Right, so that data set is known as modified because originally it was 2 different data sets, one of high schoolers and another of U.S. Census Bureau employees. And then in 1998, the data set was merged. And so the National Institute of Standards and Technologies was interested in making a data set for a number of things. And one of the key things was to allow for the automatic processing of mail delivery, right? And if you could automatically distinguish between a 0 and a 1 and a 2, then you could start to work towards mail delivery. Just like we talked about in chapter 1, the data in machine learning is really important, and people's understanding of the need for data and the models has kind of grown in parallel. Which is one reason I think it's super important to always try to be collecting your own data sets. One, it teaches you the value of collecting a good data set, and two, those data sets alone can have a very big impact. So sklearn allows you to load these in, has a little feature element in it, which allows you to load them in, and they're quite handy. And what they are 700. So really what this picture is, a good way to think about this, I'm going to draw a greatly simplified version here. Right? So they are really a number of pixels. We'll call it like that. And each pixel in this data set has a value, right? So maybe these values are gray, and then maybe these blue ones are slightly higher up. And that's going to be like a 1, right? Someone tried to draw a 1 in the shaft, or the one is a little bit less. And then you might also have like some noise out here, right? But they're a perfect grid. The images have been rotated, the images have been centered, and they've all been scaled. So they all have a little bit of white around the outside. So don't think about it as a picture. Think of it as an instance, right? So in machine learning parlor, think about the image as an instance, and then think about each pixel as a feature. So just like when we developed a way to predict the price of a house, we only looked at square footage, but there was more features that we could have looked at, right? But if in this case, we need to look at all 700. So this out here is going to be 784 pixels, and each pixel is going to have a value, right? And I'm pretty sure that they count like this. And so you can see the first several pixels are just going to be all white, and then you kind of hit the first 5, which is at the top here. And then some of these, you actually start to hit double peaks, right? So maybe that's here where you're running through the center, right? You've got something dark, and then something light, and then something dark. So you've kind of got that double peak. And again, all these machine learning models are going to do is to build a classifier based on these features. So the machine learning model does not know that it's looking at an image, but we're doing image processing by first taking our 2-dimensional picture and breaking it down into a 1D array of features. And each feature then can be between 0, which is perfectly white, and 256, which is perfectly dark, right? So your basic 256 color scheme on an 8-bit system. All right, so to begin, we want to build a 5 classifier. It's just kind of a good classifier to build because 5 is kind of a complex number, has a bit of trickery going on. And so our goal is to build a 5 classifier to detect 5s in the minced data set.